Hola, ¿qué tal? Buenas tardes. Los saludo con mucho gusto desde Michigan, desde esta su casa. Aprovecho esta oportunidad para darle las gracias al Comité Fuerza Liebre por invitarme a compartir un poco más de mi experiencia y hablar de calidad 4.0 o específicamente la aplicación de inteligencia artificial a procesos de manufactura. Es un tópico que realmente me apasiona y pues agradezco muy sinceramente que estén aquí conectados conmigo y me den un poco de su tiempo para platicar de este tópico. Aprovecho para darle las gracias a Alma, a Armi, a Patti, a Maggi, a Seferino, a Omar, al doctor Norberto López y al director de nuestro instituto, al maestro Hermenegildo Lagarda Leiva. Y pues, sin más por el momento, empezamos mi plática. Espero la disfruten. Hello, everyone. Thank you for attending to my presentation. Today, I will talk about Quality 4.0, a step forward in the zero defects vision in manufacturing. I will briefly describe how artificial intelligence is moving the frontiers of manufacturing science forward, enabling the creation of defect-free processes. My name is Carlos Escobar. I'm a senior researcher at the Manufacturing Systems Research Lab of General Motors. I investigate the application of artificial intelligence to manufacturing systems to solve engineering intractable problems. More than 4 decades ago, the concept of zero defects was coined by Philip Crosby and published in his book The Absolutes of Quality Management. At that time, and even today, it's only a vision. Traditional quality control methods based on statistics have plateaued off and shown limitations in analyzing industrial big data. Moreover, the factory of the future is driven by manufacturing systems that exhibit fast increasing complexity, hyperdimensional feature spaces, as well as non-Gaussian pseudo-chaotic behavior, which militate against orthodox traditional quality control methods. But the introduction of artificial intelligence in manufacturing has since enabled it to become attainable. Later, I will present a case study that supports this claim. And this is the agenda for the remaining part of the presentation. I will describe smart manufacturing. I will talk about industrial big data and artificial intelligence. I will briefly explain the classification principle. I will describe process monitoring for quality, the Quality 4.0 initiative that my colleagues and I developed in the lab. Then I will present a 7-step problem-solving strategy that guides its implementation and increases the likelihood of success, followed by a case study. Finally, conclusions and call to action conclude my presentation. If you have a question, please write down the slide number. I will be happy to answer your question during the Q&A session at the end of this talk. Manufacturing is a primary economic driving force. The fourth industrial revolution, or Industry 4.0, is founded on industrial big data, industrial Internet of Things, and artificial intelligence. These new technologies are propelling the new era of manufacturing, where mass customization, just-in-time maintenance, and perfect quality are the most relevant challenges posed to this revolution. Current benchmarks of quality, productivity, and innovation are very high. Rapid innovation shortens process lifespans. Processes operate at very low defects per million of opportunities. These high conformance production rates set a very high bar even for machine learning algorithms or artificial intelligence. This is my definition of Quality 4.0. It is the fourth wave in the quality movement that started more than 100 years ago with the introduction of statistical quality control, or SQC, followed by total quality management, or TQM. Then, for the last 30 years, Six Sigma and design for Six Sigma have driven quality innovation. Today, Quality 4.0 is built on the statistical and managerial foundation of the previous philosophies. It leverages industrial big data and artificial intelligence to solve an entirely new range of intractable engineering problems. Quality 4.0 is founded on a new paradigm based on empirical learning, empirical knowledge discovery, and real-time data generation, collection, and analysis to enable smart decisions. These are the areas of knowledge of Quality 4.0: quality, manufacturing, learning, optimization, programming, statistics, and a new 7-step problem-solving strategy that we recently published in the Journal of Intelligent Manufacturing. This 7-step problem-solving approach helps to successfully deploy this Quality 4.0 initiative. The main objectives of Quality 4.0 are to enable the creation of defect-free processes, augment human intelligence, empirical knowledge discovery for faster root cause analysis, increase the speed and quality of decision-making, alleviate the subjective nature of human-based inspection, and foster automation. Recent survey findings indicate that although 92% of quality leaders are increasing their investments in artificial intelligence, they do not have yet a deployment strategy. They are universally citing difficulty in harnessing these technologies, and this is reflected in the low deployment success rate, since 80 to 87% of big data projects never generate a sustainable solution. Moreover, 50% of respondents claim their inspections are mostly manual, with less than 10% automated. The problem with manual or visual inspection is that they are about 80% accurate. This poses a significant challenge for Quality 4.0. Industrial big data refers to a large amount of diversified time series generated by manufacturing systems and industrial equipment. It leverages machine learning algorithms and the Industrial Internet of Things to develop predictive systems in the Industry 4.0 era. Audio, video, images, and sensors are the most common instruments used to generate the supporting data of intelligent systems. Industrial big data is characterized in terms of 10 V's: variety, velocity, volume, void, vigilance, verification, value, visualization, variability, and veracity. Each of them poses a particular challenge that must be understood and addressed to generate a sustainable solution. For a complete description of each V, refer to the source described at the end of the presentation. According to Amazon, artificial intelligence is the field of computer science dedicated to solving cognitive problems commonly associated with human intelligence, such as learning, problem solving, and pattern recognition. The main research goals of artificial intelligence are aimed at augmenting human intelligence, taking over the tedious, monotonous, risky, mortifying, and dehumanizing jobs. Machine learning algorithms play a very important part in the structure of artificial intelligence. Artificial intelligence is transforming every industry. This technology presents an opportunity for quality leaders to differentiate and take the lead in their business segments. Broadly speaking, artificial intelligence focuses into 5 research areas. These are machine learning, robotics, computer vision, natural language processing, and expert systems. Machine learning is divided into supervised learning, unsupervised learning, and reinforcement learning. Finally, classification and regression are the main techniques of supervised learning. The boxes in gray show the technological path of process monitoring for quality. Machine learning are programs that learn from examples without being explicitly programmed to do so. They become smarter with more data through self-learning without any human intervention. In supervised learning, all samples in the data are labeled or have an associated target. Classification or pattern recognition is the scientific discipline that studies the automatic classification of an item into one category or class from 2 or more. For example, a set of pictures are labeled with a cat or dog based on the type of animal present in the picture. Machine learning algorithms learn the patterns associated to each class. Then, a pre-trained machine learning algorithm is a classifier that is used to predict the type of animal present in future unseen images. Machine learning research and applications excel at learning simple concepts, something that takes a few seconds of mental thought when a lot of data is available. For example, an inspector checking whether a critical screw is present or not in a transmission. Probably, there are already thousands of images available with the two conditions. Therefore, machine learning algorithms can be applied to automatically perform this task and increase the accuracy of the inspection. However, machine learning applications should avoid complex tasks when little data is available. Moreover, modeling complex and chaotic systems should be avoided. For example, chasing a whale. It is difficult to predict the coordinates of the next love-tailing act. Even if data is collected from the whale, such as age, gender, species, the whale can go deep, take any direction, and swim for a few seconds, minutes, or up to 90 minutes before the next love-tailing act. Before talking about PMQ, or process monitoring for quality, it is important to understand the classification principle. In the following slides, I will briefly describe it. The basic idea is to use the features or predicted variables associated to each sample to virtually project it into a hyperdimensional space where the classes can be separated by a hyperplane. A simple case is described in this picture, where a color convention is used to identify the classes. Good quality items are denoted by green triangles, whereas defective items in red circles. If three features are used, a hyperplane can perfectly separate the classes in 3 dimensions. Now, imagine an item can be projected into a hyperdimensional space to separate the classes that cannot be separated in 2 or 3 dimensions if the data contains the discriminative information. Broadly speaking, the classification principle is founded on training data. The training data, it is basically a matrix with features and the labels associated to each sample. Machine learning algorithms and the learning techniques used to train the machine learning algorithms. Training data is derived from the industrial big data. As I mentioned, the training data contains features and labels. Usually, human intelligence is required to label the classes of each sample. In the context of binary classification of quality, 1 refers to a positive sample or a defective class, whereas 0 refers to a negative sample or a good quality class. This table shows a typical binary training dataset with m number of samples and n number of features. Binary patterns can take any form, and since these patterns can exist in a hyperdimensional space, oftentimes they cannot be visualized. To convey this concept, 6 virtual patterns are presented in 2 dimensions. Again, a color convention is used, where red circles denote defective items and green circles denote good quality items. As described in the image, there are some patterns that can be separated by a straight line, upper left image, whereas there are some patterns much more complicated, lower right image, that cannot be linearly separated. The good news is that there are a plethora of algorithms that can be applied to learn the separating hyperplane, even when the patterns are very complicated. According to the no free lunch theorem, there is no a priori distinction between machine learning algorithms. In other words, there is no universal best algorithm. Therefore, several algorithms should be applied and explore their ability to learn the patterns and predict new cases. Whereas this table is not a comprehensive table, 8 diverse machine learning algorithms are included. Their diversity helps to address the coverage problem, where the basic idea is to have different algorithms to learn different patterns at different regions and dimensions. This property enables classifier fusion, another concept that we will learn in the following slides. To apply machine learning, it is important to understand the learning paradigm. Understanding the bias and variance trade-off helps to find the right amount of model complexity, where the total prediction error is minimized. upper right image. By solving this trade-off, underfitting and overfitting problems are avoided. As described in the lower right image, a high bias refers to a situation in which the data is underfitted, basically to develop an unsensitive model that predicts the mean of the observation, whereas the overfitting problem refers to a situation in which even the noise is modeled. Both issues will prevent the model to accurately predict new samples. The main challenge here is to fit the signal or the pattern in the data. This is solved by partitioning the learning data into training, test, and holdout datasets, image in the middle. Finally, the learning curves, lower left image, study the training and test errors to determine if whether more data is needed or more features or both to improve the performance of the classifier. Since prediction is performed under uncertainty, the classifiers commit errors or misclassifications. The classification performance is summarized in the confusion matrix based on 4 concepts. True negatives, when a good item is predicted good. True positives, when a defective item is predicted defective. False negative, when a defective item is predicted good. And false positive, when a good item is predicted defective. These concepts are graphically explained in the figure. Following the same color convention, if the separating hyperplane or classification threshold is 0 and the positive region is on the right side and the negative region on the left side of the classification threshold, now we can perform the evaluation. If the defective items are these red circles, then a true positive is a defective item in the positive region, here. However, if this defective item is classified as negative or good quality, then that is a false negative. Moreover, if a good item is predictive good, right here on the left side, that is a true negative. But if a good item is predictive positive, that is a false positive. Now, let's put the classification error into context. From a statistical perspective, for those training statistics, the alpha error refers to the false positives, whereas the beta error refers to the false negatives. From a practical perspective, the alpha error tends to increase the hidden factory or decrease in efficiency due to the high reinspection ratio generated by the false positives, whereas the false negatives or failing to detect the defective items is the main concern, because that is the whole point of the project, to identify and eliminate defects. Finally, as described in the image, the two errors cannot be simultaneously optimized or minimized. For example, if the classification threshold is moving this direction, the false positives will decrease. However, the false negatives will increase, and vice versa. Now, let's summarize the overall objective of binary classification of quality into one sentence. To develop a predictive system with the capacity to detect close to 100% the defective items, basically beta error close to 0, with the smallest number of false positives. A good example will be an alpha error, or the ratio of false positives smaller than 1%. The MPCD, or the maximum probability of correct decision, is a measure of classification performance developed in the lab by Dr. Mike Winsek, one of my colleagues. I use this measure to evaluate all my predictive systems. This measure of classification performance is based on the alpha and beta errors. It solves the alpha and beta trade-off by assigning higher importance to the false negatives or the beta error. It's a probabilistic measure of classification that maps its values from 0 to 1, where 1 describes a perfect separation of classes. This sensitivity analysis helps to understand how MPCD assigns higher importance to the beta error when classes are highly unbalanced. To convey this idea, a virtual sample is generated. Following the same color convention, the sample contains 5,000 good and 5 defective items. A typical situation from a manufacturer-derived dataset of binary classification of quality. In the first scenario, all the 5,000 good items are on the left side or negative region, and all the 5 defective items are on the right side or positive region. This results in an MPCD value of 1 or perfect separation as described in the table. In the second plot, one false negative is committed. In other words, one defective item out of 5 is not detected. Therefore, the MPCD score is highly penalized. It decreased from 1 to 0.8. On the third scenario, one false positive is committed, or one good quality item is predicted as defective item. Now, the MPCD score only decreased from 1 to 0.9998. Finally, the last case reflects a typical situation in which the classifier did not learn the pattern of the defective class, and therefore, no defective item is detected. Finally, the last topic in the classification principle focuses on explaining the discriminative information that features must contain for the classifier to separate the classes. To explain this concept, 6 virtual features are generated using the normal distribution. To show separation, the mean of each class is different. As described in the table, the good class of virtual feature 1 is centered at 2, whereas the defective class is centered at 5, both with a standard deviation of 1. Virtual feature 1 to 3 basically have the same separation, just different scales. If the support vector machine is applied, their separation accuracy is in the order of 92%, which means around 92% of the samples are correctly classified by the hyperplane learned by the support vector machine. Virtual feature 4 shows very low separation. It is a low quality feature. Virtual feature 5 shows a better separation with an accuracy of 97.83%. Finally, virtual feature 6 shows perfect separation of classes. Now, in this experiment, I will show you how the separation of classes improves by projecting the items into 2 or 3-dimensional spaces, or in other words, by using 2 or 3 features to separate the classes. If virtual feature 1 and 2 are combined, their estimated accuracy of 92% increases to 98.5, left top image. If the low quality feature, BF4, is combined with virtual feature 1 or BF1, still the accuracy of the best feature, BF1, improves from 92 to close to 95%, left bottom image. Finally, if virtual feature 1, 2, and 3 are combined, their accuracy is almost 100%, or basically, classes are almost separated. 3-dimensional plot on the right side shows this situation. Process monitoring for quality. It's an industrial big data and artificial intelligence-driven quality philosophy. It is a blend of process monitoring and quality control, aimed at real-time defect detection, where defect detection is formulated as a binary classification problem. Another objective of process monitoring for quality, or PMQ, is empirical knowledge discovery. This empirical knowledge is used for process redesign and improvement and to augment human intelligence to boost troubleshooting and root cause analysis. This is the conceptual framework of process monitoring for quality. Industrial big data, or process data, passes through artificial intelligence methods. First, machine learning algorithms are applied to develop a classifier, which is used to monitor and control the process. Then, feature-relevant analyses are conducted to identify the driving features of the system. This information is used to generate hypotheses to guide randomized experiments and statistical optimization, to finally redesign and improve the process. Process monitoring for quality fosters automatization, reduces manual inspections, and enables smart systems and decisions. In this slide, I will briefly explain how. A typical manufacturing system produces mostly good quality items with only a few defects. Therefore, manufacturing derived datasets of binary classification of quality tend to be highly unbalanced. The big models or BM learning paradigm is applied to develop a classifier of line. Then, a PMQ approach uses real-time generated process data to detect those defective items or true positives. However, since detection or prediction is performed under uncertainty, the classifier commits false positives, which are the alpha error, and false negatives, beta error. False negatives are the main concern, as they become warranties, whereas the false positives generate the hidden factory activities, such as rework. A good predictive solution should have high detection power at the lowest possible of alpha error. Process monitoring for quality proposes a 7-step problem-solving strategy to systematically drive innovation. Identify, accessorize, discover, learn, predict, redesign, and relearn. These 7 steps address the main challenges of the application of artificial intelligence in manufacturing to increase the likelihood of success. In the following slides, I will briefly describe each of the steps. Identify is the first step, where project selection and definition are the main goals. This step ensures data science teams are working on several relevant projects. It helps to develop a prioritized portfolio of projects with high value and likelihood of success that can be finished within 6 to 12 months. The learning targets of the project are also defined. They are usually defined with respect to alpha and beta errors. To select the winning projects, my colleagues and I developed a weighted project decision matrix approach based on 18 questions. These questions help to avoid selecting projects with low value and low likelihood of success. Please refer to source number 3 at the end of the presentation to access this list. The second step is to accessorize the process. The main goal of this step is to generate the capability to observe the process. In this step, the quality characteristics to be observed are defined based on engineering knowledge. Usually, sensors or cameras are used for this task, where industrial Internet of Things technologies are used to generate the real-time data. And these are some examples of process data. Data can be in the form of a signal, image, or coordinates. Discover is the third step, where the main goal is to transform signals or the raw data into features or predicted variables. The image on the left visually shows how signals are transformed into features. The table of the right shows some of the feature creation equations. Another activity within this step is data annotation. This is basically assigning the associated labels to each sample in the learning dataset. This is usually a manual task, although sometimes if process data can be associated to warranty data, then a learning dataset can be generated without human labeling. Labels are binary, where 0 describes a negative event or a good quality item, and 1 describes a positive event or a defective item. This table describes a learning dataset with n number of features and m samples. Learn is the next step. The main objective here is to train the classifiers and identify the driving features of the system. The big models learning paradigm is applied to develop the classifier. This paradigm addresses the main challenges posed by manufacturing-derived datasets for binary classification of quality. It is founded on statistics, optimization, and machine learning methods. More information about this learning paradigm on source 6. Since most of the times the quality patterns are not known in advance, several machine learning algorithms are trained. This addresses the coverage optimization problem and reduces dependency and enables future rules. This table shows the proposed machine learning algorithms: support vector machine, logistic regression, naive Bayes, key nearest neighbor, artificial neural network, support vector machine with the radial basis function kernel, random forest, and roost. The next step is predict. In the previous step, 8 machine learning algorithms are trained and the top performer identified. Now, the next natural step is to determine if two or more classifiers can be combined to optimize the prediction benchmark set by the top performer. In this step, an optimizer algorithm is applied to exhaustively search for a fusion rule that improves this benchmark. There are two possible outcomes. In the first one, no fusion rule improves the benchmark set by the top performer. This is shown in figure 4a. In the second outcome, a fusion rule improves the benchmark. This is shown in figure 4b. Finally, figure 5 shows the pseudocode of the fusion rule algorithm. Source 2 describes all the implementation details. The next step is to redesign. In this step, the driving features of the system are identified. This empirically extracted information is used to generate useful hypotheses about possible connections between the features and the quality of the product. Then, statistical analysis, such as randomized experiments, can be devised to establish causality, to augment root cause analysis, and to find optimal parameters to redesign the process. Finally, relearn is the last step of the problem-solving strategy. Patterns change over time in unforeseen ways. In machine learning, this is known as the concept of drift. If patterns change over time, the prediction capability of the predictive system degrades over time. To learn the new patterns, or sources of variation, or novel defects, a relearning strategy is necessary. The relearning strategy must have a learning strategy, relearning dataset, relearning schedule, and a monitoring system to ensure the predictive system is working properly. These figures illustrate the basic ideas of relearning. Figure 10 describes how to generate the relearning dataset. One source might be the rework or reevaluation station. Here, the positive results, either false positives or true positives, can be used to create the retraining data. On the other hand, as I have mentioned, warranty data can also be used to retrain the algorithms in the novel defects not detected by the classifier. In figure 11, we describe the importance of a monitoring system to alert for when the alpha and beta errors have increased, and therefore relearning is necessary. In the following slides, I will present a real case study based on the Chevrolet Bolt. In the case study, each of the 7 steps are applied to drive innovation. We will study the ultrasonic metal welding of battery tabs. This technology was highly reliable, but incompletely understood when the Chevy Bolt was launched. A weld quality is defined by its strength and evaluated based on a destructive pull test. All the welds in the vehicle, specifically in the motor, must be good for the electrical motor to function. Therefore, success requires a zero defect policy. In the first step, the project selection weighted matrix is applied. 5 projects are evaluated. Since electrification is at the core of GM strategy, project number 2, the ultrasonic metal welding, has the highest score and therefore selected. Based on plan dynamics, the learning targets for the classifier are defined as follows. Alpha error must be less than 1% and beta as close as 0 as possible. In the sensorized step, sensors are deployed to generate the signals. Based on engineering knowledge, 3 sensors are recommended. Linear variable differential transformer, delivered power, and acoustic signature. These images show the time series generated by each of the sensors. By comparing the good versus the bad time series generated by each sensor, class separation is expected, as they have different patterns. For example, the image on the right side shows how a bad weld does not generate a peak. This pattern is observed within the green and red ovals. Here. In the discover step, 50 features are created out of the signals. Here, the main goal is to develop features that contain the discriminative patterns. The learning dataset contains a binary outcome. It includes 40,231 samples with 36 defective items. This table illustrates the learning dataset. Now, in the learn step, the learning dataset is partitioned following the holdout validation scheme. 3 subdatasets are generated: training, testing, and holdout. The first dataset is used to train the machine learning algorithms. The second dataset is used to tune the hyperparameters of each algorithm and to select the final model. Finally, the unbiased prediction performance of the final model or the classifier is obtained on the holdout dataset. In this context, the main goal here is to develop a classifier with the capacity to detect the 7 defective items in the holdout dataset with an alpha error smaller than 1%. Now, the 8 machine learning algorithms are trained. Based on test results, the top performer is the support vector machine with an MPCD equals 0.8862. It correctly detected 8 out of 9 defective items in this subdataset, with an alpha error equals to 0.3%. Now, the next natural step is to determine if 2 or more classifiers can be combined to improve prediction. This question is addressed in the predict step. After applying the prediction optimization algorithm, a multiple classifier system that surpasses the support vector machine is developed. It includes the support vector machine and the artificial neural network. The prediction benchmark is improved from 0.8862 to 0.8870. In this context, the alpha error was slightly reduced from 0.3% to 0.21%. Now, the multiple classifier system is applied to the holdout dataset to obtain the unbiased prediction ability of the system. This dataset contains 9,500 samples, including 7 defective items. The multiple classifier system correctly detected the 7 defective items with only 3 false positives. The computed MPCD is equal to 0.9997. The predictive system separates the classes very effectively and meets all the requirements for the project. Now it's ready to leave the lab and move to the plan for pilot runs. In the redesign step, the main features of the system are identified using a separability-based feature selection method. The top features identified by the feature ranking algorithm were derived from the power signal. After visual inspection, as I mentioned, it was observed that the bad welds exhibited low slope. Therefore, based on engineering knowledge, a power booster was recommended to eliminate this faulty condition. This example illustrates how data mining supports engineering knowledge creation and process redesign. In the last step, a relearning scheme is developed. Based on plant dynamics, every night, the reevaluated items and any reported warranty are used to retrain the algorithms. On the other hand, if the false positives or alpha error increases to more than 1%, an immediate relearning process is executed. Figure 9a shows how the predictive system degrades if no relearning approach is included in the solution. On the other hand, the image 9b shows how the relearning scheme helps to maintain the alpha error below 1.5%. This study illustrates how machine learning techniques can be applied to detect defective welds and to move the frontiers of manufacturing science a step forward. And these are my conclusions and call to action. Traditional quality control methods based on statistics must be boosted with artificial intelligence. Manufacturing companies can competitively position themselves amongst the most advanced and influential companies by successfully implementing Quality 4.0 practices. Process monitoring for quality can be applied to solve engineering intractable problems and to move quality standards forward. Like Six Sigma the Mac, the 7-step problem-solving strategy proposed by PMQ is a systematic way to generate value out of artificial intelligence in manufacturing. Engineers, managers, and directors should be trained in PMQ. To develop a certification curricula for Green, Black, and Master Black Belts in this initiative is my future research work. If you are interested in learning a little more about the topics that I have covered today, please feel free to access any of these articles or contact me. I will be happy to talk a little more about Quality 4.0. Now, let's connect. This is my email and LinkedIn account information. Hola, espero les haya gustado mi plática y que las ideas aquí expresadas hayan encendido otras ideas de cómo ustedes pueden mejorar sus áreas de trabajo a través de la aplicación de inteligencia artificial. Este mensaje va dirigido muy particularmente a las personas que laboran en la industria de manufactura de nuestra ciudad, ya que siendo esta una de las principales fuentes económicas de Ciudad Juárez, tenemos el gran compromiso de hacer que nuestra ciudad sea reconocida por su ingeniería avanzada, más que por su ubicación geográfica o su mano de obra. Habiendo dicho esto, se abre el foro para preguntas y respuestas. Arriba, Fuerza Liebre.
Listo, Carlos, muchas gracias. Está súper interesante todo lo que nos platicas. Realmente que con estas pláticas, cómo vamos aprendiendo. Bueno, la gente, al menos yo que no estoy en el medio de la industria, me quedo sorprendida de tantas cosas que se están dando actualmente y que hace 20 años, cuando estábamos más o menos en la escuela, no, bueno, yo un poquito más de 20 años cuando estaba en la escuela, ni por aquí hubieran pasado, la verdad. Muchas gracias por esta plática tan interesante que nos acabas de presentar y sobre todo para los muchachos, ¿no? Que están ahorita en clase y que vean todo lo que pueden llegar a hacer ellos también en un futuro no muy lejano al momento de salir, todas las herramientas que le está dando en estos momentos el TEC, cómo las pueden aplicar, qué pueden mejorar y nada, no sé qué más quieras agregar.
Bueno, pues primero que nada, otra vez darle las gracias. Desde que se inició la sociedad Fuerza Liebre, pues me invitaron y me sentí muy atraído por la pasión, especialmente de Alma, tuya, Maggie, de Army, de cómo este grupo tienen esta visión de apoyar el desarrollo de las liebres, de sacar adelante la industria manufacturera de nuestro país. Así es que pues esa pasión la sentí y pues otra vez es un honor tener esta oportunidad de haberles compartido un poco más mi experiencia. En realidad traté de hacer una plática, poner todo lo que he aprendido, digamos, en los últimos 5 años. A lo mejor fue mucho material, pero pues bueno, si les interesa, ahí están las fuentes, aquí estoy yo a la orden, cualquier duda que haya, pues ahorita podemos platicar de ella, o ahí puse mi correo electrónico, con gusto comparto un poco más de esto y me mantengo conectado.
Muchísimas gracias, Carlos. Por cuestiones de tiempo ya vamos a tener que dar por concluida nuestra plática, pero yo estoy segura que los muchachos, una vez que ya hayan digerido toda la información y que ya lo estén ellos aplicando un poquito, a lo mejor ya algunos estén dentro del área, ya estén trabajando y que vean qué es lo que pueden hacer con toda la información que nos has proporcionado, aunado a lo que se les está dando ahorita de herramientas en el TEC. Estoy segura que vas a tener varios correos por ahí. Muy segura de esto. Pues sí. Muchísimas gracias. Gracias a todos quienes nos acompañan a través de Facebook Live por acompañarnos en esta tarde. Muchas gracias, Carlos. Claro que seguiremos en contacto. Ya estamos pensando en una entrevista ya un poquito diferente para más adelante. Y pues nada, ya sabes que esta es tu casa. Estamos en Casa de las Liebres. Y
claro que sí, pues es un gusto poner un poco de mi conocimiento al servicio de este grupo Fuerza Liebres y pues especialmente de todos los contactos. Es un honor y pues gracias otra vez por esta oportunidad y pues estamos en comunicación.
Claro que sí, muchas gracias a ti, gracias a todos quienes nos acompañaron, muchas gracias Norberto por hacer este esfuerzo posible para poder llegar a todas las liebres que nos están viendo en estos momentos. Muchas gracias, que tengan muy bonita tarde. Hasta luego.
Hasta luego.
Bye.